This video demonstrates an economical antenna gain and radiation pattern measurement system which was developed by Team IsoTropic Thunder at the University of New Brunswick. The accuracy of the system is found to be plus or minus 0.5 dB for a dynamic range of 13 dB plus the gains of the two antennas in use. The system is also reproducible for less than $1,300. The design and operation of the system will be presented along with measurement results for a homemade Pringles cantenna. Okay, so let's take a look at some of the hardware associated with IsoTropic Thunder. First off, we have our power supply, which takes an AC input and gives us all of our DC output lines. We have our microcontroller, which acts as sort of the heart of the system and interfaces with most of the rest of the hardware. We have our gain detector, which basically computes the gain between its two inputs. One input is fed through two attenuators, a 20 dB pad and a 60 dB pad. The other is fed from a bandpass filter and a low noise amplifier. Finally, we have our frequency synthesizer, which is configured for the 2.4 GHz ISM band. During a measurement, the microcontroller communicates with the synthesizer via custom-made serial communication lines and configures it to sweep its frequency. The synthesizer has two outputs, one of which is fed through attenuators to the gain detector. The other is fed through a long SMA cable to the transmit antenna, which is mounted roughly 3 feet above the tabletop. The signal travels roughly 10 wavelengths or 1.25 meters at 2.4 gig to the receiver antenna, which is mounted on the antenna positioning system. The receiver antenna is connected through another long SMA cable to the low noise amplifier. The output of the low noise amplifier is connected directly to the bandpass filter, which is in turn connected to the detector. The detector determines the gain between its two inputs and outputs a DC voltage, which is sampled by the microcontroller. The microcontroller is also interfaced via high current outputs to a stepper motor, which rotates the upper platform, which is connected to the lower platform through a lazy Susan bearing. This is done via a belt drive assembly, which couples the motor shaft to the upper platform. A tensioning assembly is also included, which keeps the belt tight throughout an entire rotation.
The microcontroller serves the user interface through a regular Ethernet cable to a laptop. The user interface, which is a web page, can be accessed by using the default IP address 192.168.0.200. The web page allows the user to make gain measurements based on the 3-antenna method, view the associated gain results, and execute a radiation pattern measurement.
The first step when making a measurement is to calibrate the system, which is done by connecting a 20 dB pad between the two antenna feed cables. Calibration is completed by clicking on the Calibrate Now button on the web page. Let's measure the gain of a Yagi antenna, a log periodic dipole antenna, and a monopole antenna. Enter the distance between the first two antennas and click on the Capture button. This yields the combined gain of the two antennas. Exchange the Yagi for the monopole antenna and enter the distance separating this antenna combination. Click on the Capture button. Finally, exchange the log periodic dipole for the Yagi, enter the distance, and hit Capture. The antenna gains now appear in the gain results block.
Now, let's take a radiation pattern measurement of the Yagi antenna. Scroll down on the user interface to the radiation pattern block. Since radiation pattern data has yet to be captured, press the Measure Pattern button now. The antenna positioning system rotates with an angular resolution of 1 degree. For accurate measurements, the antenna should be polarization aligned and matched to 50 ohms. To reduce the effects of noise, at each step, several readings are taken and then averaged together. Measurements made by the gain detector are highly phase sensitive. This sensitivity can be suppressed by sweeping the frequency of the synthesizer. This has the effect of sweeping the phase difference between the detector input signals. Averaging measurements taken at each frequency results in a phase-insensitive gain measurement. After this test is complete, the system reverses a full rotation to untwist any cables. A plot of the radiation pattern is now displayed. The collected results can be displayed by pressing the Show Raw Data link. This data can be copied and pasted into another program for further processing. The plot can be saved by pressing the Save Graph link. The image will be opened in a new tab or window and can be saved as a PNG image file.
To make things interesting, a Pringles cantenna was constructed for testing. A somewhat damaged Pringles can forms the housing for the cantenna. The signal is fed in through a bulkhead SMA adapter. A director element is built into the lid of the Pringles can. The feed has been tuned for resonance at 2.4 GHz. Although the inside of the can is not conductive, the back is and serves as a reflector element.
To accurately characterize the cantenna, we've moved into an anechoic chamber. We start by taking a radiation pattern measurement. Although it's difficult to see in this video, a Yagi is being used as a transmit antenna. And here we see the radiation pattern of a Pringles cantenna.
Now, let's use the 3-antenna method to determine the gain of the cantenna. The Yagi and the monopole will serve as the other two antennas. We begin by measuring the combined gain of the cantenna and the Yagi. Next, we exchange the Yagi for the monopole and measure the combined gains of these two antennas. Finally, the combined gain of the Yagi and monopole is measured. Note that antenna 1 is the Yagi, antenna 2 is the cantenna, and antenna 3 is the monopole. The gains obtained for the Yagi and the monopole are well within 0.5 dB of those obtained using an Agilent PNA. Therefore, we can say with confidence that the gain of the cantenna is approximately 5.6 dBi. The system developed by Team IsoTropic Thunder is capable of making accurate antenna gain measurements, high-quality and automated antenna radiation pattern measurements, and is easily reproducible for less than $1,300. IsoTropic Thunder was used to characterize a Pringles cantenna. It was shown to have a forward gain of approximately 5.6 dBi. This is impressive since the cantenna can be built at home for approximately $15 and includes a delicious snack in a variety of flavors. We hope you enjoyed the presentation and thank you for your time.